So welcome everyone to today's shared conversation. Today is the third in our three-part series around post-quantum cryptography. Today's session is PQC Algorithm Arcana. I'm Alexis Kolek. I'm the Director of Education for SHARE, and with me today is Tim Hill. Tim is the Vice President of Engineering and a Distinguished Engineer with Rocket Software. And we've been talking all week about, or throughout the course of the series, about digging deeper into some of the details of the algorithms involved in post-quantum cryptography. Tim is here to bring that to us today. So Tim, I know you've got a lot of ground to cover. The promise we've made about lattice topography is finally here, and I'm going to turn the floor over to you to begin today's presentation.
Thank you, Alexis. So I guess I'll start with that word, arcana. In the dictionary, it means specialized knowledge that is mysterious to the uninitiated. And needless to say, I think for all of us, quantum mechanics, quantum physics is pretty mysterious, whether you're initiated or uninitiated, things that we just can't get our heads wrapped around. But the good news is that I'm not really here to talk about those kind of counterintuitive properties of quantum mechanics like superposition or entanglement. That's not what this is about. We're here to talk about more familiar topics, right? Like computers and algorithms and regulations to a certain degree. So today is just meant to be kind of a teaser for the more in-depth conversations we'll have at the Share Blueprint Conference. And I'll start out today with a bit of level setting up front to make sure we have a common framework for discussing the crypto concerns around quantum computing. Then I'll introduce some of the approaches that are being taken to get past those concerns, get to a post-quantum computing state of affairs where we can kind of enjoy the benefits of the technology and what it can do and be a lot less stressed about this whole vague cryptographic insecurity that it's brought to the table. So we'll also dive into those algorithms designed to withstand quantum attacks. So without further ado, I am legally required to start with a joke. In this case, a quantum joke. I decided to give cats a break, living or dead, the day off as the butt of all quantum jokes. But as I just mentioned, the punchline of this joke of they simultaneously do or don't understand is, again, sort of the way we all feel about quantum computing. And there are a lot of applications of quantum computing in various fields, but we're going to focus and are focusing on cryptography, on code breaking, on the impact of quantum computing on our IT infrastructure. So let's first do a quick review of two major categories of encryption that are used today. And this kind of sets a foundation for us. So symmetric and asymmetric. And it's pretty simple. So symmetric is symmetric. It uses the same key for encryption and decryption. And only using one key, of course, kind of makes this method fast and efficient. And it's therefore a bit of an ideal choice for encrypting large data sets or real-time data streams for that matter. But symmetric encryption is typically used for data at rest, like stored files and databases that need strong, continuous protection. And the downside, of course, is that the key that you use has to be shared and somehow between the sender and the receiver. And that can make key management a bit challenging, especially over unsecure networks. You always have to assume that somebody is intercepting everything you send. Asymmetric encryption, on the other hand, uses two different keys, right? One is the public key, which can be openly shared. I can send that to anybody. And then they can use that public key to encrypt a message or encrypt data that they want to send to me, the recipient. So I have the private key, and that's only known to me, the recipient. And that key can decrypt whatever they've encrypted with the matching public key. So that's how asymmetric encryption works. And that has the advantage of not requiring a single key to be securely shared between the sender and the receiver, right? And there are also hybrid approaches that use asymmetric techniques to securely exchange or at least agree on a symmetric key, and then that symmetric key encrypts and decrypts the actual data. So key exchange, as I just discussed, doing key exchange is sort of the foundation of online confidentiality. When your browser connects to a bank or you use a VPN to your company network, the first step behind the scenes is always the same. Both parties, both ends, have to agree on a shared secret key. And they have to do so without that key ever crossing the wire in plain text. Okay, that's the challenge. And for the last few decades, of course, two families of mathematics have kind of made this possible. One is RSA key transport, where the sender encrypts a random secret under the recipient's public key, like I just described with asymmetric encryption. Security then rests on the difficulty of, in this case, factoring large integers, which I'll talk about more in a moment. And then the second key mathematical approach was the Diffie-Hellman elliptic curve approach, where both parties exchange public values, normally their public key, and then the shared secret emerges from a sequence of steps they both take involving discrete logarithm problems and finite fields, elliptic curves, a lot of math words, but the gist of it is, in that case with Diffie-Hellman, the secret kind of emerges from that. The key thing here is, no pun intended, is that our whole public key infrastructure, really, like any secure website where you're doing banking or buying something with a credit card or VPNs, the whole Internet of Things, pretty much everything we touch daily mostly relies at some point on asymmetric encryption algorithms, which depend themselves on the difficulty of certain math problems, the discrete logarithm problem, the integer factorization problem. And these problems are called one-way functions. And their strength is based on how long would it take to reverse that function. And usually in these cases, it's thousands or millions of years for a computer to reverse that function. And hence, we have security. We're pretty confident if it takes thousands of years with the most powerful computer, it's probably going to be okay for my bank information. But let's take a closer look at integer factorization and where, how implementations do that, where they multiply very large prime numbers together to create keys. So that makes it easy for computers to encrypt information. They're just basically doing multiplication. That's very easy. But it's very hard for a classical computer to factor, to reverse that process, to factor those large resulting integers without having a key to drive that. Hence, it's called a one-way function. Very easy to encrypt, very hard to decrypt without the key. But then in 1994, a mathematician named Peter Shor published a paper, and all of a sudden, quantum computing became a national security issue. Shor described a quantum algorithm, meaning it's an algorithm that could be implemented on a quantum computer. He defined one that could quickly factor those huge numbers that are products of those big primes. Well, that put the whole world's encrypted information at risk. And you've heard of algorithms like RSA and ECC, elliptic curve, and Diffie-Hellman. In a quantum computing world, those algorithms, currently at the heart of everything, are completely broken. That's the most important thing to understand. They're completely broken. What about the symmetric encryption side that I talked about? Well, those are actually also vulnerable to quantum computing, but less so, significantly less so. Grover's algorithm is one that could be implemented on a quantum computer to use superposition principles to speed up a brute force attack against symmetric keys. And basically what it does is it cuts the problem in half, right? Which sounds pretty significant, cut the problem in half, right? But it's not. It just means that you need to double the key size to effectively make it quantum safe again, right? So going from AES 128 to AES 256 is the current assessment of what it takes to be quantum safe on the symmetric side. So how big does a computer, a quantum computer, have to be in order to break asymmetric encryption like RSA, as I've discussed? So, and the term used is, when will we have a cryptographically relevant quantum computer? CRQC, if you like acronyms. So there is some frequently quoted research from 20 years or so ago that concluded 4,099 qubits, quantum bits called qubits, that's what you would need in order to factor a 2048-bit RSA key using Shor's algorithm. And that stirred up a lot of concern, but in reality, that figure refers to logical qubits, well-behaved qubits that are perfectly stable and error-free. So generally, you can think of a logical qubit as requiring 1,000 or more physical qubits to be able to address all the error protection that's necessary in quantum computer technology today. So how long would it take to break 2048-bit RSA? It depends, but mostly it comes down to the number of qubits available. And once we reach a sufficient number, it will theoretically just be an overnight job to break RSA 2048. And keep in mind, this is a job that, today on current computers would take billions of years to brute force. So billions of years versus an overnight job is sounding pretty scary. And it will, in fact, though, really require on the order of millions of physical qubits working together, backed by, good error correction and so forth, to maintain these thousands of logical qubits through trillions of operations. The bottom line is we're nowhere near that today, at least publicly known. Today's publicly known quantum computers have anywhere from just a few up to around 6,000 physical qubits. So remember, 6,000 physical qubits, that's maybe enough for about 6 logical qubits on our way to 4,000 logical qubits. So we're not there at this point, at least not in public exposure. But a realistic concern that you've heard about before, and I'm not going to dive into, but I'll mention, is the harvest now, decrypt later problem. And this is really talking about bad actors recording encrypted traffic today and saving it, and then they can decrypt it once quantum computers arrive. And data with long confidentiality requirements like government secrets or medical records or financial data, this is already at risk. People can be recording this data today, and many government agencies do already record this data today. So granted, a workable quantum computer is probably still well beyond what's currently possible. The gap between theory and deployable hardware is still pretty big, but it's clear that it's a question of when and not if. It's an engineering problem at this point. So migration to quantum safe encryption is the obvious strategy. And by the time we can actually build a sufficient quantum computer, we have to be totally off of RSA and the like. Now, we're not going to spend much time on the regulatory environment today. It's been covered before, and I believe will be covered more in other blueprint sessions. But just 2 notes, the US government has established some clear requirements through NIST guidelines with some key milestones for the deprecation of 112-bit security algorithms by 2030 and mandatory transition to quantum resistant systems by 2035. And the UK has similar roadmap requiring discovery phases by 2028 and high priority migrations by 2031 and full transitions by 2035. So plenty of regulatory framework for this. So to capture what I've said so far, the core problem any new algorithmic approach to PQC, post-quantum computing, the core problem it has to solve is that classical public key crypto, RSA, ECC, that dies once Shor's algorithm runs on a large quantum computer. That's it. And that's because those algorithms are based on hard math problems that will be solvable with quantum. But these 4 families that you see here on this page, these 4 families of algorithms are based on mathematical problems that are believed, at least, to be hard for both classical and quantum computers. Now, we're not going to turn this into a math class, but let's spend a minute today on one of these, the main winner of the NIST PQC competition, which used what are called high dimensional module lattice equations. Now that's a mouthful. What the heck does that mean, right? Well, a lattice is just a number theory concept, which we're not going to pretend to dive deep into, but as a gross oversimplification, and kind of just to give it a sense of why it's a crypto-worthy hard problem, let's see if we can go a little bit into this. So imagine kind of a perfectly regular grid of dots, like a piece of graph paper, and it stretches infinitely in every direction and in any number of dimensions. So every direction, any number of dimensions. So that multi-dimensional grid is called a lattice. And every dot in that is a lattice point. And to get from one dot to another, you always move in whole number steps in some kind of fixed direction. So if you think of it like a map of New York City, roughly as a two-dimensional lattice, right? A lattice is going to have infinite dimensions, but a two-dimensional lattice, map of New York City, and with each street intersection being, let's say, a lattice point. Then directions might be north 2 blocks, east 6 blocks. Easy peasy, right? So of all the problems you can pose about a lattice structure, the most natural turns out to also be the hardest, and it's that shortest vector problem. Okay, in 2 dimensions, it's easy. You can draw it, a picture on a piece of paper like we just did mentally with a map of New York. You can see the answer immediately. In 500 dimensions, think about that for a second if you want to, lose your lunch. But in 500 dimensions, which is the scale used in cryptography, by the way, no known algorithm can solve it without exponential time. So now you're, because it's trying to find its way, find the shortest path through this 500 dimension lattice. So again, setting it up is easy. And that means encryption is easy, right? But brute force solving it without full information is extremely hard. Again, decryption without key knowledge is extremely hard. That's what makes this a good, hard problem that is hard both for classical computers and for quantum computers to solve. So NIST actually standardized on 2 lattice schemes. The primary standard for general encryption is called ML-KEM, Module Lattice Key Encapsulation Mechanism. They love those acronyms. And you may have heard of it before. As you can see here, it was formerly called Crystal's Kyber. For those of you who've heard of crystals for key encapsulation. And this is the most versatile PQC algorithm family. And it supports not just signatures and key exchange, but also fully homomorphic encryption. And homomorphic encryption means you can do computation on encrypted data without decrypting it first, which is really cool, but that's a whole separate conversation. This is the algorithm that will protect, key exchange and TLS, VPNs, messaging protocols, every system that currently relies on Diffie-Hellman or RSA key transport. Key encapsulation, KEM, is different from the key exchange. If you're familiar with Diffie-Hellman, in Diffie-Hellman, both parties contribute to the shared secret. Usually they contribute their public key to get that ball rolling. In KEM, one party generates the secret, encapsulates it, and pushes it to the other by putting it inside their, encoding it within their public key. So the result is the same. Both parties establish a shared secret without ever transmitting it. That's the goal in both these cases. And of course, the main purpose of key exchange is to securely establish shared secrets that can then be used to derive keys. And those keys can then be used with symmetric algorithms that we talked about earlier to transmit information in a protected way. So ultimately, symmetric algorithms tend to be used to encrypt, the bulk of data because they're more efficient than public key algorithms. So the trade-off between these two, between classical versus quantum friendly is quantum has larger keys, larger ciphertext. As you can see on this chart, the keys in the ciphertext are significantly larger. And this has impacts, right? This will impact things like TLS handshake size, which matters. If you're like on a mobile network with small transmission units or IoT devices with constrained memory or applications that have high frequency API calls where the handshake overhead really matters, having larger ciphertext under ML-KEM means that it effectively means that the encrypted data packets used to establish the secure communications are significantly bulkier than the traditional cryptographic algorithms like ECC and RSA. But they're bulkier because they have to resist quantum computing attacks. Instead of relying on a few very large numbers or relying on a simple coordinate on an elliptic curve, for example, ML-KEM uses multidimensional lattices, as I described earlier. That requires transmitting large arrays, usually of things like polynomial coefficients and noise that they inject into that. That's for an even deeper discussion. But that's why those packets are bigger, is because they're transmitting more information in order to protect from quantum computing. So as you can imagine from what we've been discussing, the transition to post-quantum cryptography is going to have a few challenges. So one is these really large key sizes that I was just discussing. PQC algorithms require keys and ciphertext that are far larger than RSA or ECC. And that means an increased memory footprint, which could potentially strain some constrained environments. It means higher bandwidth consumption, which impacts network performance and scalability. And in terms of performance, quantum safe algorithms demand usually significantly more computational resources, right? And that leads to increased latency, which can impact real-time applications or high throughput applications. And that can be especially problematic for embedded systems, let's say, and IoT devices with limited compute capacity, or things that are battery powered. Battery powered workloads can face accelerated power drain under heavier crypto workloads. These are little edges that people don't necessarily think about up front. The harvest now decrypt problem later that we talked about, where adversaries actively intercept and store encrypted data today to use later, means migration urgency is now, even before quantum computers are fully realized. The whole ecosystem, the entire technology supply ecosystem chain has to align. You can't do all of this yourself. The whole ecosystem has to align before any kind of broad adoption is really feasible. That means things like hardware security modules have to be updated or replaced to support new algorithms. Major operating systems, they've got to build in PQC algorithm support, which they're already starting to do. Protocols, libraries, firmware across the stack require coordinated updates, and coordinated updates are not easy. And then integration systems have to run PQC and classical encryption simultaneously during this coming transition period, right? Hybrid cryptographic architectures are going to be necessary, but they're going to increase the protocol and operational complexity effectively. And greater complexity raises the risk of implementation errors and therefore security gaps, right? So interoperability has to be maintained across the legacy systems and modern systems throughout this transition. So in the big scheme of things, the place to start with is discovery, inventory discovery, crypto inventory. Before you can secure your systems, you have to know where your cryptographic dependencies exist currently. Algorithms, key sizes, certificates. You need to prioritize. Not all systems need to be migrated at once. Rank your assets basically depending on their risk profile or their data shelf life. You need to plan. You need to have a roadmap that is a practical migration strategy that emphasizes crypto agility, I could spend a whole talk on the ability to swap cryptographic algorithms without redesigning the entire system. That's very important. It's called crypto agility. And you need to be able to pilot, deploy these things in a development or test lab before you try to roll out into production. So that's that's it for today. Hopefully this has given you a taste for some PQC topics. At the Blueprint meeting, we're going to dive into even more topics like hybrid solutions during the transition where they're running classical and PQC algorithms in parallel. We're going to talk more practical takeaways for your enterprise migration. We're going to look back at some of those hash-based algorithms that I kind of skimmed over today, because those are viewed as sometimes as a conservative fallback for some of the high assurance signature use cases like firmware signing, for example. And of course, there'll be lots of discussion about the path forward. So thank you again for your time. I look forward to seeing all of you in Pittsburgh.
Thank you so much, Tim. I have to admit, it was a little bit like watching 2001: A Space Odyssey. You have that moment of clarity and realization where everything makes sense and all the pieces fit together. But if you walked out and tried to explain it to somebody else 5 minutes later, I'm really not sure how well that would go. So
well, 1 out of 2 is not bad.
Very deep dive into a very complex subject, and for getting to lattice topologies, which we've been promising for 2 sessions.
Oh, okay.
I would also love to see this technology in action. If you're familiar with the Douglas Adams universe, what deep thought would have done with quantum computing. I will open it up to our audience to see if they have any questions. You can enter those in the Q&A tool. Of course, we have a request for the slides, so we'll work on that. While that's coming in, I did want to ask with regard to some of the key areas that you mentioned. Some of our previous sessions, we've talked about addressing the concerns of harvest now, decrypt later, right? And focusing on your key workloads. We've talked about the artifact size. You mentioned performance considerations. And I think there's this impression that once we get to quantum computing, that somehow that's also going to be more sustainable in this space, but it's not necessarily, right? We're still talking about a massive amount of power, not only to run these computers, but also now to handle the requirements of passing these large artifacts and storing all of these data components. Can you talk a little bit about what's going to change from a performance consideration as we enter this era?
Yeah, and more importantly, what are we not talking about with performance? When we talk about performance, we're really not talking about the quantum computers. The quantum computers are going to do their thing. That's a whole separate discussion. We're worried about performance in all of our world of conventional computers, where we have to encrypt our data that we transmit every day using more powerful encryption algorithms like I've described here, like ML-Chem, for example. But these have larger payloads. They have more setup time. They require more CPU cycles to set up. They're more complex in that sense. You're transmitting large data structures instead of much smaller data structures. All of those hit performance at one level or another. Are they dramatic? Well, it depends on the application as to whether they're dramatic. Only the application can answer that. But they certainly exist. They will be a real thing over time. I'm sure these will be optimized the way that our current algorithms have been optimized in hardware, for example, et cetera. But initially, its performance is going to be a non-trivial issue.
And that's definitely, we've talked in some previous sessions about the need to involve the entire organization in a discussion about what the shift to address PQC is going to mean, right? It's not just your security team. It's not just your network team. It's not just your systems engineers. Everyone is going to have a conversation about how this is going to impact the flow of business, right? And how that data is going to be managed. So that's a really important point.
Exactly.
One other item that you mentioned is there are certain kinds of data that are exceptionally long-lived for an organization from a compliance perspective or other requirements. What would you say people should be considering as potential long-lived data sources that they might want to prioritize and move to the front of the line?
Well, obviously government secrets can be long-lived. You've seen how long it takes the government to declassify anything, usually decades. So those are right at the top of the list. Your health records. Yeah, you may not want your health information shared any more 5 years from now than you do today. And it's, we live a lot more than the 5 to 10 years between now and when this will be real technology. And there are many other corporate, I wouldn't call them corporate secrets, but intellectual property secrets. I don't think Apple would want some of their iPhone intellectual property secrets uh, totally distributed on the internet today or totally freely available. Not that most of them aren't already, but that's a separate issue. The point is, there's plenty of situations like that where we want to protect things for more than the 2 to 10 years that we have uh, before this becomes a daily reality.
Fantastic. There is a note from Tom Cosenza, who presented the first session here, that he couldn't have presented lattice encryption any better, and he didn't. So congratulations on that, Tim.
Thanks, Tom.
We're right at the close of our session, but thank you so much, Tim, for being with us today. For our attendees, we encourage you to take advantage of the recording of this session and the other portions of our PQC series on the share.org website. And please do also learn a little bit more about our Blueprint event that's taking place as part of Share Pittsburgh coming up this August. We have a great overall program for you, and the Blueprint event offers a really unique opportunity to dive in. And as Tim mentioned, get more hands-on with this and have the chance to walk away with an actionable plan for how to address these kinds of situations. So thank you everyone for being with us today. Have a great rest of your day, and we hope to see you in Pittsburgh.
Thank you.